Good morning, folks. This is the week 4 lecture one. And on the agenda for today, I'm going to be discussing essentially two things. One is some miscellaneous comments, some leftover from the things that we have done in the past 3 weeks. And then my final problem on shells, which is going to be a single pressure vessel that is in your book. So let me go ahead to first of all, the shells that we use for surfaces, the main difference of them with solid element is that through the thickness of the shell, through the thickness of that surface where shell elements are laid, the stresses are zero. In other words, the normal stress through that depth and the two shear stresses through that depth are zero. That is not an assumption, of course, for solid elements. Solid elements, those stresses are not zero. Therefore, they're more versatile and they're more general than shell elements. But shell elements are very robust because you can take complicated structure and based on if that assumption is valid, solve them with shell elements. Now, the other thing I want to tell you before I move on to this concept of different type of elements, etc., is the fundamentals of what you have learned in the past 3 years should not be forgotten. For example, if somebody gives you a problem like that, so you have two rigid blocks vertically standing, as you can see, and then these are attached together with a single bar of material 3, and then the block on the left is attached to the wall with two bars or two bars of possibly different materials. Now, notice that a bar actually loaded is essentially a fancy spring with this stiffness, where A is the cross-section of the bar, E is the Young's modulus, and L is the length of the bar. So when you look at material 1 and material 2, these are the two horizontal bar on the left side. Each one of them will have a stiffness. You find the stiffness based on this formula, add them up because they are in parallel. So now you have replace the two bars here with a single spring, and then you have a spring in the middle. So now you have two springs in series, and what you do is you find the stiffness, equivalent stiffness of this whole structure as K1 plus K2, which is in parallel, and then K3, which is in series with the other two through this formula. So you should not rush to a finite element package in order to find the displacement of this block when you apply force. That is all you need. Now, the other thing I want to tell you is about the mesh conversion study. I told you that it's so easy to generate good-looking nonsense and garbage. Okay, so if you do a finite element analysis of a structure once and just rely on the answers that you've got, you might as well tear it and throw it in the garbage bin. Okay. You really have to make sure, one of the things that you have to make sure is that the results that you got do not depend on the mesh that you selected. And the idea is that take a finer mesh, but the finer mesh in critical areas. Don't go and take a fine mesh in an area which is inconsequential. So you have to have developed some kind of a feeling for where the critical areas are. Get the results for that particular mesh, and then refine the mesh in that area and compare the results in that same area with what you got before. If there is significant difference between the two, you might as well forget about the first one and then starting refining the second mesh. You do this thing until things don't change that much. And the question came up, what do you mean things don't change that much? Well, that's a judgment call that you have to make. But what I have in mind is maybe something between 5 and 10%, depending on the culture of that organization that you're working, or the level of confidence that you have. 5 to 10% difference is kind of acceptable, at least to me. Okay, that's what mesh conversion study means. Now, let's go to the concept, the three type of elements that we have looked at. We started with things like this. Now, this is the default element meshing in the CATIA program, in the generative structural analysis. Now, they are of the linear or parabolic type. Essentially, they're pyramids like that. And CATIA calls it octree tetrahedral element, which is rather, this octree is specific to CATIA. Generally speaking, these are called tet elements or tetrahedral elements. I'll call or pyramid elements, as I call it. So now there is the more sophisticated version of this, which I call shoeboxes or brick elements, and these are called in CATIA. You do not have access to these in generative structure analysis. You can generate elements like this, like shoeboxes, in the advanced meshing tools, but not. It requires some work, and I have some videos posted on it, but I don't expect you to be able to do elements of this type. You have to know what they are. You have to understand what this thing means, but I don't expect you to do a problem with these elements, anyways. Notice that these are 4 node, these are the 8 noded, these are 20 noded, I believe, and yeah, we counted, it's going to be 20. I call it brick, hexahedral, hex elements, these are shoe boxes, these are all used in the literature. Now there is something compromised between these two, which are called wedge elements, by the way. These are also available in CATIA, but in the advanced meshing tool. Now, shell elements is the counterpart of what you saw, so they go on surfaces. That's why they look like triangle, because you can draw that. You can draw it in a piece of paper. You can draw it on a surface. So there's the linear variety and there's the parabolic variety. Now, I call them shell elements. Some people call it triangular shell element. And CATIA call it octree triangle elements of the two varieties, linear and parabolic. Now, there's also the counterpart of these in the advanced meshing tool, which is 4-sided. They call it quad element, I call it 4-sided or quadrilateral element. Now, these have to be done with the surface mesher or advanced surface mesher in the advanced meshing tool. Okay. Beam elements, you know what they are, linear, parabolic. I told you that this parabolic, I noticed that at least in the older version of CATIA, they were not always activated to be able to use. But anyway, we can use linear. These are so versatile that it really doesn't matter between these two. The only advantage of doing parabolic ones, if actually they are activated and available, is you have a curved beam. Then it probably, if you use linear, you have to use a lot of elements through the curvature area. But with parabolic one, a few will suffice. Now, one other thing that came up is some people ask me, what do you mean by distorted element? Well, let me go back here to these cases, either this or these. When you look at, let's go actually to, for example, this shell element, which is the same thing is true for the solid elements. If you see an angle which is very close to 0, for example, if this angle is very close to 0, just hypothetically, pretend that this was 1 degree. Notice that this element becomes very long in one direction. Same thing here. If an angle is very close to 0, which means automatically another angle is going to be very close to pi, this is going to be a highly distorted, very skewed kind of shape. Okay, it's like this. Visualize it. These are called distorted elements, and they are bad. So that's what we mean by distorted element that can cause a problem. Now, of course, distortion does not make sense here. There is no angle in that sense that you can find. Now, let me also remind you that beam elements, the linear one, for example, just has 2 nodes. Each node has 6 degrees of freedom. Shell elements, for example, the linear one, triangular one, triangular shell elements, linear shell element, it has 3 nodes, and each node has 6 degrees of freedom, just like beams. But solid elements, the pyramids, or the tets, or the tetrahedrons, each node has 3 degrees of freedom. Rotation is not a degree of freedom in the calculation. Okay, so that's something that we have talked about it many times during the past 3 weeks. And, yeah. Okay, so let's go ahead and do our very last shell type problem. I'm going to do this. Some of the formulas that every mechanical engineer should know for the rest of their lives if they stay in mechanical engineering or engineering. These are thin-walled pressure vessels. So if you have a pressure vessel here with the thickness, wall thickness of T and mean radius of R, and it's internally pressurized, for example, Then the hoop stress, there are three principal stresses: the hoop stress, tangential stress, the axial stress along the line, and the radial stress, which is in the depth direction, in the thickness direction of the shell. Now that is zero, very small actually, and because we solve these things with the shell elements anyways, that's assumed to be zero. Now, for the case of a sphere, you already saw in the homework from last week that it is actually PR over 2T, hoop stress. Well, they're both in plane stresses, principal stresses, or PR over 2T. They both follow this kind of a thing. And of course, the radial through the thickness is zero. Now, we want to solve this problem, but I want to take a 45-degree sector on purpose because I want to be able to create a local coordinate system and stuff like that we did in the previous sessions, such as last week, last tutorial. This you're expected to use the most appropriate element, which is in this case going to be solid element. Oh, no, oops, no, shell element. Okay, and these are many planes of symmetry. Now, obviously, if you cut this thing through the surface, right in the middle, if you cut it through the surface, the top and the bottom will behave exactly the same. And if you take any sector, such as a 45-degree sector, 30-degree sector, 90-degree sector, you have the same pattern that you get here repeated all the way around. Okay. Now, on purpose, I'm going to take 45, not 90. Okay. Now, when it comes to modeling this thing with shell elements, and that's what you have to do, you have to create that surface, and there are different ways of doing it. I'm going to do this problem two different ways. The first way is by just creating, for example, the surface directly, okay? And I come back and then repeat that thing by creating the solid and extracting the solid surface of the solid, because I have no control over how you're going to be doing something like that on the test. I'm going to do all of that. Okay, so let's keep this thing here. Before I go any further, now when it comes to applying restraints, symmetry restraint, you use this table. We already know what this thing means. And yeah, so I'll get to that later on. Okay, so let's go ahead and start with the part. And since I'm going to be creating the surface directly, okay, I don't want to start in part design. I'm going to go to generative shape design. Let me see. I have customized my interface so that all I have to do is to click here, or you can go here to start, and then on the shape, under generative shape design. So on the vertical plane, I will sketch basically this L, inverted L, and the dimensions are this whole thing is 40, so that's 20 inches, and the mean radius is 6. So 6 by 10, okay? So let's go here, something like that. Okay, let's dimension these. So this is 10. And this is 6. All right, exit. And we're gonna revolve this thing. Now remember, we're trying to create a surface, and this is the main toolbar for creating surfaces. This one on the left is extrude, revolve, and some primitives, basic primitives here. So I could have done this thing, by the way, with this guy, with this cylinder guy. I could have done it right here, right there. But I'll revolve it. This is the sketch, and I'm going to rotate it or revolve it about the z-axis by 45 degrees. Okay, there we are. Okay, so we know that this is made of aluminum. Let's apply material to that. I keep losing my material right there. Apply material on that part. Okay, and that's pretty much it. I'm not going to use any fancy elements, so we'll not go to the advanced meshing tool. I will just go to oh, one more thing before I do. Because of the nature of the way I made this thing, I drew this L and revolved it. These two are essentially do not have a seam along that line. If you want to join it, be my guest, but it's not going to make any difference. Okay, so just leave it the way it is. Okay, so we go to analysis and simulation, generative structure analysis. It's a static analysis that you're doing. Let me change the rendering here to what I like. It looks like that. And we're using shell mesh, shell elements right there. You see, octave triangle measure. So this is all in the model manager with the toolbar, with the traffic like this. Yeah, right there. So because of the way I did this thing, this is all going to be meshed at the same time. We didn't have to join it, but right there. Let me make this thing 0.5. And it's linear. Okay, you can obviously parabolic is more accurate. And if you want to see your mesh, put the cursor there the usual way, right click, mesh visualization. And there we are. Okay, let's deactivate that. Okay. Give it the thickness, wall thickness. This is the wall thickness. See that? 2D property. 1D properties for beam, 2D properties for shell thickness, 3D properties. It's not automatically for us unless you deleted the mesh and you want to create the mesh yourself. So 2D property on that face. The default, the thing that I did last week was 0.1. So what is it here? Let's check this. Thickness of 0.1. You're lucky. I don't have to change this thing. And it's just a thickness. Materials property pick. You say okay. Very good. And notice that it's created right here. By the way, if the wall thicknesses were different, you put the cursor there, right click, local 2D property. That is not the case for me right now. Okay, good. So let me hide these sketches. And I tell you why, because the next step is, for example, to put restraints, right? If I, just hypothetically, if I wanted to put a clamp, I'm not supposed to put a clamp, but I'm saying, notice that nothing can be picked because there's a sketch sitting there. So what I'm going to do is going to hide the sketch. Good. So user define restraint. Okay. Let me uncheck all of these. Check all of these. On this edge and that edge, in the global sense, global direction, these edges sit in their YZ plane, therefore there is no displacement in X, and rotations are opposite. Good. This bottom one, let's uncheck all of these. This bottom edge is with respect to sitting in the global XY plane as a symmetry plane. So as soon as I say XY, no displacement in Z, rotations opposite. My problem comes on these two edges because these two edges are neither in the XY plane, XZ plane, or YZ plane of the global system. So I really need a coordinate system here. And to create a coordinate system, you can't do it here. You have to go either to part design or generative shape design. So I have to go back here. That's where I see in the tools toolbar, access system, right there. Okay, you click on this. It says, okay, you want to create a coordinate system? No problem. But tell me where do you want its origin to be? For example, I can say the origin is at that corner. It says, okay, it's right there. But the global direction and the local direction axis system are the same. I don't want that. For example, I want this thing to rotate by 45 degrees. But you know what? In this case, it's very easy. I can also say my x-axis, I want it to be this line. That does the same thing. So it's entirely up to you how you want to do that. I selected the x-axis It puts it there, and essentially it gives me coordinate system. I could have rotated it too, but that's fine. All right. So now we're going to go to analysis. User defined string. Uncheck all of these. Now notice that we're going to be using not the global system. First of all, these two edges. We only use these two edges. Oops, not the whole thing. These two edges, just the edges. Not the global system, the user system. And it says, okay, user system, go pick it. So it's right here. Okay, right there. And in that system, those two edges that I picked lie in the XY plane. So no translation in Z, and rotations are exactly the opposite. And we say, okay, good. Don't forget to save your part and your analysis, please. Both of those we need for this problem, okay? If it's a part, we need the part, cat part, and cat analysis. Later on, starting tomorrow, starting Thursday, we're going to start assembly. We have a product file, we have a bunch of part files, and we have the analysis file. All of them we want. Any one of them missing, we'll have a problem marking your paper. Okay, so the pressure inside, interior pressure, you just click on this. See that? Click on that. This is pressure. Which two faces? I want this face and that face. And just watch the direction. This is not correct. This is suction of the tank. So I put down minus 100. Let me see, what was the value of the pressure here? 100 psi. So I put a minus. Now this becomes inflating this thing, or pressurizing it from inside. Say okay. Good. Very good. Run it. This tells you that your element probably are not good. It says a bad shape element. Okay, no problem. I understand that. I understand that. Let's look at it. It's supposed to blow up. And it does blow up in the sense that it becomes inflated like that. And it's just like a balloon that you're, kind of blowing up. You don't see any movement of the vertical bit because this is a flimsy cap. That's a flimsy cap. And there is a displacement here, but you can't see it because this is so flexible that actually overwhelms the displacement of this guy. Now, let's look at the displacement. There we are. If you double click on it, actually you can see average ISO, change the rendering to material shading right there. And notice that if you put the cursor, you see very little displacement. You can see it, very little. Whereas this is 2 inches, for example. Now, if you want to see the displacement here, there are ways to do it. Let me remind you how it is. For example, I can go here, deactivate this, and I can go and say, all right, show me or create a group, surface group, for example. These are the groups, different kind of making it. There is one that is surface, here, surface group, on that surface. And then when you activate translation, it says, don't show me everything. Double click on that. Don't show me everything. On the selection tab, show me the surface group right there. You can see that there is displacement and the colors pop up here. All right. Now, one last thing I want to show you here is that let's look at the principal stresses. So not one Mises, but see over here, expand them. The second icon, principal stresses. And if you zoom in, you see they're both tensile, and I bet axial one is half of that. So this is what? This is almost 2,400, and this is almost 5,900. That doesn't surprise you because the theory says axial one is half the hoop point. And in fact, if you put the P, R, and T that I had, it's going to be very close to that number that you had. If not, then you go change the size of the element, go from brilliant to parabolic, etc. As a matter of fact, let's see now. P was 100, R was 6, so that is 6,000, right? 600 divided by 0.1. 6,000. So this number is supposed to be 6,000, but it's 5,970. Okay. If you go to parabolic, and let's try it. If you go to parabolic, probably it's a little bit of improvement, not much. I mean, I don't know. We'll find out. Okay, show me the principal stresses. Let's check it in. Oh yeah. Oh, actually, this. Oh, this is on the top, so you have to go to the middle of the tank. It should be around 6,000. Right there, 6,120. Anyway, so that takes care of this. I want to repeat the same problem, except that I will be using solid elements. So let me kill this and that. I'm going to start with the part. So, for example, because we're going to be creating a solid object, I might as well go to part design. On that face, I will sketch. Or there's two ways you can do it. You can draw a rectangle and revolve it, or you can draw a sector and then pad it. That's entirely up to you. So on this, so let's do that. Okay, so let's go and dimension these things. This is 6. And this is 10. No, that's 20. Okay, so exit. And then shaft it about the z-axis by, let me see now, by 45 degrees. There we are. Okay, let's apply material to this thing. Where is it? Apply material, aluminum on that part. We say okay. And now we're going to go and extract the top face and the side face. So obviously I have to go to generative shape design. Remember, you go it like we do it like this. You go to shape and generative shape design. Okay. Look for the extract icon right there. Extract. It's in this operations toolbar, the third toolbar on the left side. It's right here. Extract this. Okay, no problem. And do it again. Side. Okay, you can hide this. These are the surfaces that are extracted. Now notice that you cannot delete those. You cannot delete these because these surfaces depend on it. You can hide them. All right, yeah. Right there. Okay, now you better join these because if you don't join it, when you mesh it, only the top one is going to be meshed. And then when you mesh it again, only the side one is going to be meshed. And there's going to be duplicate nodes at the seam. And there are other ways to fix it, but when you join it, that doesn't happen. So I'm going to join it. So this and that. Notice that, yeah, so right there, these are joined. Okay. Now, yep. So we're going to go to generative analysis and simulation, generative structure analysis. Because there is a solid object in hiding, that's going to get meshed right away. So I am doing a static analysis, but that solid object must go deleted. And the corresponding 3D property must go deleted. The rest is just like before. So let's go ahead and finish it one more time. So mesh it. Because we joined these things, everything is going to be meshed at the same time. Linear or parabolic, only that's parabolic, no problem. And then thickness, 2D or 1D property, you click on it, 0.1, that's good. And the restraints, let's change this thing to user first. So this edge and that edge lies in the global YZ plane, no translation in X, and rotations opposite. Okay, and then the bottom, I wish there was a clear all button here. This guy lies in the global XY, there's no displacement in Z, and rotations are opposite. Now for this side, these two sides, I need the axis system, so I cannot do it here. So let's go to the part, get the tools toolbar right here, axis system, at that corner, and I'll do it a different way than what I did in the one a few minutes ago. What I can do is I can put the cursor there, right click and say rotate 45 degrees. That does the same thing, except that, yeah, good. So if you look at it now, it achieves that. In other words, these two edges are in this YZ coordinate system. Okay, so back to the analysis. Again, click on the user define, uncheck all of these. Okay, select the edges that you want, this edge and that edge. Not global, user, and says go pick to user system. Actually, look at the bottom left corner here, it gives you an idea of what you need to do. See that? It says select an axis system associated with the part. So that is what I want. And then in that coordinate system, there is no displacement in X because that is the YZ plane, right? Symmetry. And rotations are exactly the opposite. Apply the pressure. You gotta be careful here because notice that this, you will have to do it on both faces. If you go this route, you have to do it on both faces. Okay? Otherwise, just put it on one. In the previous case, because I rotated it, or what do you call, revolved it, there was no issue with putting it on both, but here it doesn't. So, I mean, nothing exciting is going to happen. It's going to be exactly the same result, pretty much exactly the same result as before. So you can look at the, for example, one meter stress, let's get the displacement, yeah, that number was also the same there. Okay. All right, folks, so we are done with shell elements right now. For maybe a week, we're going to be away from beams and shells, but then we're going to come back the week after. That's going to be week 5, I believe, towards the end of week 5, and we will do all 3 of them at the same time, participating in a finite element model, namely beams, shells,